let me tell you, there is a difference. The temperature of the cold roller is is less than half of the melting point of the metal being rolled. Right now, it's an alloy of tin and bronze, 5% tin. And now calculate the force on the roller. So you have to calculate the force on the roller in order to find out. This is my roller here. This is my roller here. And then this is my very rough sketch. Okay. So this roller has a motor. This motor is running the roller and calculate the power provided by the motor and the force per roller. I would say use this formula. Force, like, do you remember pressure equals to force per unit area? So force equals to pressure times area. And you will ask me, Professor, what is the area on the roller? Look at the contact surface. This is the contact, okay? I'm just highlighting it. This whole is a contact. This is known as L. This arc length, I would not say it's an arc, but it's like an arc which is pushing the material, bringing it inside the roller, and then throw it outside. Okay, so this is L times W. This is my W. Okay, the whole width of the roller. That is the area under the roller. What is the area under the roller? I will say W times the L. You understand that? And P is the average pressure on on the plate by the roller. And you will ask me, Professor, how do you calculate the average pressure? So I'm going to take you over this formula. So let me show you. Yes, I'm going to take you over here. Let's grab this yesterday, last time lecture, and then I will show. Please note down. This is the roller, and you will use this formula. But let's see, is it a large roller or a small roller? This is, if this is a small roller, then you will not use this formula. You will use a different formula if it is a a small roller. Yes, this is the formula for a small roller. So first of all, you have to verify whether it's a small roller or a large roller. How would you verify? Look at this formula. Okay, so what is the delta? Delta is just a symbolic expression. H average over the length, where is the arc length under the roller. So you will ask, Professor, what is H average? So H average is the height in the beginning. This is my beginning side, okay? Height in the beginning or height at the back, height at the front, thickness. I will say thickness, okay? Sometimes you can understand this as a thickness or height. It doesn't matter. So you should know like this. So in the beginning, the thickness is 2 millimeter and the final thickness is 1.4 millimeters. Can you open your calculators and help your professor? What do you get for this one? 3.4 divided by 2, 1.7. Okay, now you will find out what is L. What is L? And then I will take you to the formula. Formula for L is not difficult. This is L. Look. The L is square root R, square root R times delta A. So I'm bringing those slides into your knowledge. You don't have to derive this formula. You just use them for solving the question. So what is my L? You will tell me, Professor, L equals to square root radius of the roller times the delta H, final minus. What is delta H? You will tell me, Professor, this is beginning height minus final height. 2 minus 1.4, which is zero point 0.6 millimeters. Agreed? So let's find out L. What is R? If you take a look in the data, R is 75 millimeter rollers. So I can write down here 75 times zero point 0.6. Can you open your calculators? What do you what do you find for this answer? Is it 6.7? Please verify with your answer. Yes. Student says 7. That's good. Now let's grab this formula. Let's grab this check. Whether this check is for a large roller. If it is a large roller, you will use this formula. If it is a smaller roller, you will use this formula. And how do you check? By delta. Delta, if it is very, very small than 1, it is a large roller. If it is greater than 1, it is a small roller. Do you understand the difference? So let's do the math here. You will help me. Okay. 1.7 divided by, what is this? Is it 0.25? Less than 1. So this is a case of large roller. So you will use this formula. Okay. Up until here, is this clear? Okay. So you have to check. If you see this quiz question, you will see similar question. You have to go step by step. This is the first step. And if you finalize this is large roller, use this formula. So force per unit rule. So let's do this. I will say force per unit roller is L times W. So you can see P average times area, P average times area of the roller. P average equals to 2 tau flow. P average is 1.15 sigma flow or stress flow, or you can write down mean flow. And here comes the knowledge from the more stress circle for the von Mises criteria. And y bar flow can be calculated by this formula. K epsilon n over what is epsilon? Strain ln of final thickness over initial thickness. Final thickness is how much? 1.4. Initial is 2. What do you get? Do you get 0.36? What is my n? The strength, the index n equals to 0.46. And I can write down. So let's find out sigma flow, which is y mean flow equals to K7. How much it is? It is 720. 720 megapascal. And N equals to 0.46. 0.46 divided by N plus 1, which is 1.46. And if you do the math, you should be able to get this 354 megapascal. Can you open your calculator? Let me know you get the same answer. If not, then I will redo this. Maybe it's different. What answer do you get? I have to verify. I got 308. So it means this is not the answer. So the right answer is 308. Do you get 308.233? Yes, 308.23. Okay, now this is the Y flow, but this is the 2 tau flow. You remember there is a shear stress criteria from Mohr stress circle. So 2 tau flow, so which is equal to so I can write down P average equals 1.15 times 308.233. Now it is correct. 1 plus. So 1 plus mu. How much is the coefficient of friction? 0.1. 0.1. Okay. 0.1 times 0.1 times the L. L is how much? 6.7, right? L divided by 2 times average. Okay, open your calculators and help me. What do you get? Do you get the average pressure per roller equals to 423.76 megapascals? Please verify. Yes, you get the same? Thomas says yes. James says yes. Dimitri says Malala. Yes, that's good. Very good. You guys are understanding. I'm glad that you see you have to pick up this formula. Once you find the P average, then you have to use this formula. Okay? Area under the roller. Look at the picture, the sketch I drew here. This is the area. The arc length times the width of the roller, which is W. This is under rolled, the manufacturing under being rolled. So that area W times L. Okay, guys. So area, I'm gonna write down 423.76 into 10 to the power 6 times length. Arc length is how much? 6.7, right? And the width of the roller, was it? Yes, width of the roller is 10 millimeter. 10 millimeter. Let me check. 6.7 millimeter. So can you convert it into 10 to the power negative 3 times how much? Width is 10, 10, 10, 10, 10, 10, 10 to the power negative 3. Can you do the math? And how much do you get? Do you get this answer? I got the same answer. Do you get the same answer? Now, after you find the force from the roller onto the workpiece, this is per roller, okay? Then you have to find out the power. The question is, how do you find the power per roller? Let me show you. I think I gave you this slide here in the yes, you remember power per rollers torque times omega. Torque equals to force of the roller times the moment arm. So this is the roller and this is my radius and this is the L by 2 here. L by 2. This is the neutral point. We call this as a nip point here. Okay. And then it brings the metal inside and then the stress. This is the situation here. So now look over here. Torque equals to force times L by 2. And then omega. You see, this the torque. How will you find out omega? Omega can be found by two methods. So look, the tangential speed of the roller is given, and you know very well it is given 0.8. So you know very well that if a roller is moving with a tangential speed, and if you are given the r, suppose this is a tangential speed, okay, v of the roll, and r is given, how do you find out radian frequency? You will tell me, Professor, tangential speed equals to r times omega. You agree with me? And omega equals to tangential speed of the roller divided by the radius of the, which is given. The speed of the roller is given how much? 0.8. 0.8 meters per second divided by roller radius. How much is the roller radius? 75 millimeter. Let's convert it into meters. Can I write down like this? What do you get? Can you help your professor? And that value, you're going to plug it in over here. 0.8 divided by 0.075. And if you calculate the torque, I think it should be equal to, let me grab this again, and you will help me in doing the math algebra. And that should be equal to 1.01 kilowatts per roller. And if you want to find out the horsepower, this is the power. This is the, I'm sorry, this is, I messed up because this is the power. This is the torque. Do you understand? because torque times omega is the power per roller. And now you can convert it into horsepower because you know 1 horsepower equals to 0.746 kilowatts. And if you do the math, you should get 1.35 horsepower. Do you understand this question? Will you be able to solve this problem in your quiz? Yes. How much do you get? Let's see. What do you get? 28392 times 6.7 times zero point 0.8 for per roller. Oh yeah. I'm sorry. You look, Pamela is helping me. You see? Divided by 2. I forgot. Okay. You understand the mistake? People may mistake, but I will not reduce my grades because I'm a professor. You will reduce your grade if you do the mistake. Should I be lenient in grading your exam? James says, I hope so. You agree? Divide by 2. Okay, that's good. We have found the answer. This is kilowatts for roller. And now you can find out the uh, so about the plot the pressure in the nip is the same thing which you have to you look over here. The pressure looks like this. Remember, as the forging in the middle, you have a maximum pressure, and in the extreme ends, you have a smallest pressure. So let me show you. Yeah, I think I got to mention that the minimum draft is 0.75. So you see, you can further reduce with this coefficient friction, you can further reduce the thickness. So it's a good start that it says that you can tell how much thickness can be achieved in the final thickness. So look, if it is 2 initial thickness minus 0.75, what is that? 1.25. You can achieve with this coefficient of friction, you can achieve this much thickness, but how much are we reducing? We are reducing to 1.4. Like we are still inside the window of that thickness range. You see my point? So that's a good check. Another check you can do, what is the phi maximum angle of acceptance? Zero point 0.1 radian, alpha is 5.2. or this is a different example, 3, example 4. This is the maximum pressure in the center of the L. Some of the defects you can create in the rolling uh, shear stress, you will self-study these defects, okay? But during the rolling process, the strength increases after the rolling process because the grains, they are more strain free and intermediate grade. So although we assume that the width does not change, but a little bit it changes if you see from the top view. Some residual stresses due to frictional constraints for small rollers, the tension in the beginning, compression after the neutral point, it because the material flows fast. Okay, this material flows faster. This velocity is smaller here. Some types of defects are pictured, sketched here. Wavy edges, zipper cracks, edge cracks, alligatoring or piping. Rolls can deflect under the load. Rolls can be crowned. You see, you can have successive rollers in order to create more forging pressure or rolling pressure. This is a complex design where you can reduce the friction. Smaller the roller, smaller the friction. Larger the roller, larger the friction. So you see the smaller roller, but it has been backed up by bigger rollers. With that, we have finished the rolling manufacturing process. And now the next slides we are going to start today is the machining. Have you heard about lathe, milling, Have you heard about these drilling, milling, shaping, sharpening, planing, boring, turning, lathe machine? Who has used lathe before? Raise your hand. You have used lathe? You? And who has used milling machine before? Wow, that's a good. And drilling, I have done the drilling. You might have done the drilling too. So, but that's good. And I will have a field trip today over there. You will go during the class time after 10 minutes. I'll take you to the machine. Um, there is a MET department. Uh, they have a lot of machines, so you will have a knowledge about the lathe machine. And do you know you can use these processes? Lathe machine is, let me bring it inside my handouts. These are the processes you can perform on the lathe machine. Yeah. So let me start from here one by one. Our machining slides. This I'm not giving you in the quiz. I'm just asking you to prepare extrusion and rolling. I will give you this in the following week once I start the problems. You see the old machine shop, but now we have latest machine shop where machinery is ship formation. So I will focus on this part. When you are doing the processes, you will focus on mostly on this section. How, what is the chip area? How much chip is coming out of the workpiece? So you will see, we call this MRR. In the question, you will see how do you find out the material removal rate, MRR. Is known as a material removal rate. And you see, I think this is, I have to redraw the sketch. In the bottom, it's like a cutting tool. The cutting is happening right over here. This is velocity, chip velocity. You see when the workpiece is coming and then the material is flowing inside. I will go into the detail and my focus would be more on the tool workpiece interface. How much chip is being removed. This is the process known as the turning. When you are turning down the diameter of a workpiece, which is a circular round workpiece. In the lathe machine, we have round workpieces. You see, such a big lathe. Maybe for marine engines. I'm not sure, but this is a very custom made machine to to turn down the shaft from a large diameter. You see how much chip is being produced here. But I think in Q308 we have very small machine. I will take you over there as well. You know, last time what happened when I taught this class, students were given a workpiece to perform some processes like turning, knurling, boring. So this time I might give you a small assignment, but let me think about it, okay? With your consultation, I have to see. Discontinuous chips that the material is brittle. If it is continuous, then it's more ductile material. They are very hot, so we should not touch them. Okay. I think I drew this picture here. It's different. Please draw this picture. This picture is talking about the milling machine. The the tool is removing the chip. So there are certain angles. This is known as zeta, clearance angle. It is not in contact with the workpiece. It is not grinding to reduce the friction. And then if you take a look, this is the thickness of the undeformed chip. And this is the thickness of the chip. As I mentioned, my focus would be more on the chip thickness, chip flow, chip velocity. That's why I need to explain you some technical terminologies. And if you draw a line here, this angle is known as phi. What is phi angle? This is phi angle, which is called as the shear angle. Shear means like cutting happening at this angle. Okay? Shear angle. And if you draw a vertical line, then this angle is the alpha, rake angle of the tool. Tool has the front face of the tool. It is at an angle with a vertical line. We call this angle as rake angle. We will go more about these in our problem solving. And now, last item is cutting velocity. The tool is moving or the workpiece is moving. That speed is known as the cutting velocity. Okay, this is sufficient. For now, it's just a review. I want you to understand these six terminologies: clearance angle, undeformed thickness chip, chip thickness, shear angle, rake angle, and the cutting velocity. So, in general, when the rake angle increases, then the shear angle decreases. So, if this goes down further, like this is the 2, okay? This is very large angle. You see alpha 1 is smaller than alpha 2. Then what will happen? This decreases, this further decreases. We will talk more about it, okay? Okay, I'm to end the lecture to take you the field trip.